Hi, this is for our class, the STEMCATS class that's looking at zinc. Just to kind of give you an overview, because we've had some questions about why then the MRO in the crayfish, we see an increase in activity with the high zinc exposure. So I want to relate this to what we found before with when we reduce the calcium in the bath, we also get the increased spontaneous activity. But we got to go over some of the basics again, just to make sure we're following through on understanding some of the concepts. So a lot of this understanding about the action potential came from this little critter here, the squid. It has a very large axon, so people could put electrodes inside the axon and outside the cell and actually understand the electrical events in axons. So they use this giant axon. It's not a giant squid, it's a giant axon. They can put electrodes inside of it in the presynaptic nerve, and they can put an electrode in the postsynaptic nerve, such as here and here, and they can actually understand the shapes of the action potential. This is how this all occurred, and that we know that at some resting membrane potential, you depolarize it, you open up voltage-gated sodium channels, it goes up, these voltage-gated sodium channels close, or inactivate is a better word. But you have another threshold around here that opens up voltage-gated potassium channels. So potassium goes out of the cell, counteracts the sodium going in, and that potassium, as it goes out, then can make the cell more negative. In some cases, we see this undershoot, or after hyperpolarization, as you do in the squid, but not in all neurons. Okay, so the idea is, again, here you see sodium channels open, more sodium channels open because you hit the threshold. They inactivate. It's used as closed, but it's really, the word should say inactivation. And then voltage-gated potassium channels, they really start to open over here, so this diagram isn't completely clear. They open up around in here. It depends on the type of voltage-gated potassium channel. And then as they open, potassium goes out. That brings the cell back to a more negative value. Sodium, which is a plus charge, goes in, so that depolarizes the cell. Okay, this is all based on the Nernst equation, which is the potential is equal to, say, of ion differences across a cell. So if you have positive charges on one side, more so on one side than the other side, what kind of electrical potential would result? This is the equation that determines that. So R is the gas constant, T is temperature, Z is the charge of the ion, F is Faraday's constant. Ln times the out of the concentration, say, of an ion outside with the concentration of the ion on the inside. So you can figure out what's called the equilibrium potential for sodium or potassium. So just think of this as potassium, equilibrium potential for potassium, and you have low potassium on the outside and higher potassium on the inside. If you take that ratio and you take the ln of it, it'll be a negative value. And then you times it by these constants, keep the temperature the same, R and T and F, and Z is the +1 charge, then you'll have a negative value. So the equilibrium potential for potassium with the concentration gradient higher on the inside and low on the outside will be a negative value. Now for sodium, the equilibrium potential for sodium is higher outside the cells than it is inside the cell. Let's say 120 versus 10. And just flip this around the other way, for potassium, okay? So if you have a higher sodium on the outside than you do on the inside, this will become a positive value. So the equilibrium potential for sodium is a positive value. What does that mean? The equilibrium potential is what the driving force for that particular ion is. So sodium wants to go to a positive value, and potassium wants to go to this equilibrium potential for the negative value. This doesn't explain everything, so people use the Goldman-Hodgkin-Katz equation, because now what's different from the Nernst equation is you take in permeability. So at rest, the cell is not that permeable to sodium or chloride, but it's more permeable to potassium. So this p-value would be a greater value for potassium than it would be for sodium or chloride. This means it's going to follow more so towards the equilibrium potential for potassium than it would for sodium. But if you start to open up sodium channels and it's now permeable to sodium, what's it going to do? Well, it wants to follow then the equilibrium potential for potassium. And we just told you that's going to be more positive values. So if you go back up, when you open up sodium channels, and the equilibrium potential is up here for sodium, it wants to go to the equilibrium potential. If you close sodium channels and now you have potassium channels open, what does it want to do? It wants to go to the equilibrium potential for potassium, which is down here. So it's all about the driving gradients and the permeabilities. And this is what's different from the Goldman-Hodgkin-Katz equation than the Nernst equation, is you have a contribution of the permeability of the ions, and that changes then the membrane potential for considering all these different ions. Okay, when you think about an ion channel, think about there's negative charges, glycoproteins on the outside as well as the inside. Here's what's referred to as like a gate that could inactivate and like close the channel with electrical change. So you get the idea that there's some voltage sensor, which is amino acids that are positive or negatively charged. So when you change the membrane potential across, the charge of these amino acids then are influenced by the charge across the membrane, and they can close the channel or open the channel. Okay, so this is interesting about calcium and the action potential. If you have calcium inside, let's just look at these models. This is a bullfrog sympathetic ganglion. You get the action potential, voltage gauge, sodium channels open, boom, and then it comes back down. If you have calcium around, it comes down and looks like this. If you take calcium away, it doesn't have this, it takes longer to hyperpolarize, and then it doesn't hyperpolarize as much. And they actually did these recordings from a model in the sympathetic ganglion, and it actually mimics this quite well. So it's interesting, it became wider and it didn't hyperpolarize as much. Now what does all this do to? This is just reducing calcium outside or blocking the calcium channels. Also, if you give an electrical stimulus, you inject current into the cell, control cells, you get some firing. If you do it in blocking calcium activated potassium channels, which we will talk about in a minute, so calcium comes in and activates the potassium channel, which would bring the membrane to a more negative value. If you block that, the cell is more excitable. So the idea is, here's your equilibrium for sodium, here's your equilibrium for potassium. And you open up the sodium channels, it goes to the equilibrium for sodium. You open up potassium channels, it goes to the equilibrium for potassium. This is just conductance to show you sodium goes into the cell here, and potassium starts to go out of the cell here. So it's just conductance. Okay. And the squid, this has been worked out with the squid and understanding what's happening with these membrane potentials. A lot of this work has been done. So this is to show you that there's different types of action potentials in different cells. Every cell shows a different shaped action potential. So Vm is the membrane potential, and this is the current, Na, the nanoamps. The membrane potential, picoamps, and current. Okay, and this is a membrane potential here. Just want to show you a few things. So here's an action potential in a neuron, dopaminergic neuron. Boom, boom. It somewhat has a little hyperpolarization, not much. Amplitudes might be different, but you see the shape of it. Here's another neuron, a Purkinje cell. This is inside of your cerebellum in your brain. And you see that, look at the time difference. 5 milliseconds, half a millisecond. Very fast. This one shows more hyperpolarization. It tells you down here the types of currents. So red is sodium. See big sodium, and then there's calcium that comes in. And that calcium that came in changes how the shape occurs. It prolonged it. And now calcium over here, there's not much calcium that comes in. There's a lot more sodium that came in. Okay. And here's some other neuron, another neuron. This one's very small responses and pretty wide on the calcium. Okay, and here's another neuron, and you see the differences here too. Whoops, I want to go back. This is another current that's shown here. This is a calcium activated potassium channel. This is kind of interesting. So calcium comes in, and then that activates the potassium channel, and then so you get sodium, you get the the calcium that comes in, this negative thing, but then that activates the potassium channel, so potassium goes out. And that's the potassium conductance. So outward is up and inward is down on currents. So current is sodium going in, this is potassium going out. This is due to the calcium activated potassium channel. So calcium coming in activates the potassium channel and causes potassium to go out. That's separate than the voltage gated potassium channels that are in red. So beginning to understand the calcium that comes in can activate a potassium channel. Here's some examples of action potentials with different potassium channel blockers. Remember I told you when you start to open up the sodium channels it depolarizes, but you have potassium channels that will open. Well, you have multiple types of potassium channels. One type opens really fast and then closes. Another type of voltage gated potassium channel has a delayed opening and then it closes slowly. This is a drug that blocks the fast activating potassium channel, and we see at a low concentration, 30 micromolar. You put that in there and it doesn't come back down as fast, right? Because you blocked the potassium channel. Give it a much higher concentration and you've blocked more of the potassium channel, and it takes much longer for it to come back down because mostly sodium's coming in, but there's also maybe calcium that's coming in too and keeping this wider. This drug, TEA, blocks that slow opening potassium channel. So when they block that, it maintains this depolarization state for a long period of time. And this is 25 millimolar compared to these concentrations. Okay, so what happens with low calcium in your body? These two signs are common with low calcium. Chuz-Vogt sign, I don't know how to pronounce it correctly. You touch on the facial nerve right here and you'll get these contractions in your face. If you put a pressure cuff on someone's arm and they're low calcium, then they get this Trousseau sign. Their arm starts to contract and their hand will twitch in. And this is due to the neurons being hyperactive to mechanical deformation on them. So they're hyperactive. The thought is that low calcium, if you don't have calcium around, that low calcium coming into the cell then can't activate the calcium activated potassium channel. And this is what keeps it after hyperpolarization, this negative response, right? So calcium comes in, activates potassium, potassium goes out, that keeps it more negative, right? With potassium going out. So this after hyperpolarization is thought to be a lot due to the calcium activated potassium channel and also the shape. So if you block it, it now goes the other direction. It goes like to the black. Here's an idea of what happens with current injections, and you get these changes. But if you block it, you will actually have more activity because you're not hyperpolarizing the cell as long. So it's kind of interesting thought process. People have looked at why low calcium, and this relates to our project, because zinc 2+ probably blocks the calcium channels and is the same kind of conditions as low calcium. So some ideas about why calcium causes these changes. Well, people think that calcium actually blocks the voltage-gated sodium channel somewhat. So here's just changing the calcium concentration outside and looking at the current with an injection into the cell. And they actually found out with higher calcium, they got a smaller current. And this is the sodium current. So this is thought to be that the calcium, actually high calcium, can block the sodium current. So low calcium allows the sodium current to exist better. So if we had zinc and it was blocking the calcium current, channels, that might have an impact on the shape of the action potential, because it might be doing the same thing as altering the sodium channel. Okay. Pay attention here. These are the same concentrations, calcium and barium. So what they do is give this voltage step, open up voltage-gated channels, calcium channels, and then they look at the effect. If you use 20 millimolar calcium, you get this calcium wave, and it comes back down. If you use barium, you also get this current trace, and it's wider. So it's kind of interesting. There's the effect of switching out calcium for barium. Let's change over here to understanding. Remember they channels, I told you they have this glycoproteins and they have negative charges. So this is one idea that was out there for a while, so you understand that calcium can screen that negative charge because it's a 2+. That changes how the ion channel, the voltage-gated channel, senses a change in potential across the membrane from top to inside over here, outside to inside. If you're screening these charges, the channel doesn't respond as well or as much. So if you took it away, low calcium, then you have more of a negative charge that the channel is going to respond. Remember, it's the channel that opens and closes, and it's the conformational changes of the amino acids inside. So the idea is if you turn this all sideways, you could look at outside to inside of a cell. Let's say the inside of the cell is -60, and outside is, by definition, then 0. And this is with calcium screening that negative charge. If you take away the the screening, now all of a sudden what the channel senses is a more negative potential, and it's going to change the delta between the inside and the outside, and this is what really matters because this is what opens or closes the channel. So that's an idea that people have. So they think that calcium screens this, and you don't have that starting off negative value, so you're like back to what would be 0, and you could have some low calcium here, and you might be screening some of that charge. It really, the impact is then on the channel itself. Hypercalcium, the idea that they found with recording sodium currents is they think that high calcium actually blocks the voltage-gated sodium channel, somewhat competes for the sodium ions, and that's why you get a different lower sodium current with high calcium. Okay, hypocalcium. If we take away, so we have this right now, if we take away the calcium, then what happens? We don't have as much blocking of the sodium channel, so we might get a better current. That's one idea there, and that could then be a factor. So less calcium, less activation of calcium-activated potassium channels. They also have an idea that the membrane can become leaky and more excitable. That's interesting. Alters resting membrane potential, and less action on the sodium channel if you alter the calcium. But think of us, if we're adding zinc, it's like you might be adding more calcium to it. So you might think it's blocking the voltage-gated sodium channels. Alright, so this is just ideas of changing concentrations and seeing how that affects the pores of these ion channels. Now, in the animal physiology class, our neurophys class, we actually do something like the MRO preparation, but we do it on a joint receptor called the cortitonal organ, and we're going to actually use zinc on it next semester. But just think about the same kind of thing, that this joint moves back and forth in the walking leg, and that stretches a strand, and that strand are sensory endings like this, like these right here, and changing that, the environment on that causes these stretch-activated ion channels in the sensory endings to change. So here's kind of like the MRO. We stretch it for 10 seconds, we record the activity, but there's many neurons in this preparation compared to the MRO. So we put a suction electrode here, just like you do in the MRO, and stretch it, and then see what happens. Those are the little sensory endings that are inside the cortitonal strand. We have different endings that are in the muscle fibers on the MRO. Instead of having this little cap over the muscle fibers in the muscle, these free endings just go into the muscle fiber. But it's the same idea. You're opening up stretch-activated ion channels in the endings. When you stretch the muscle, sodium goes in, depolarizes it. If it gets to a threshold, then boom, fires an action potential and travels down the axon. So here's a model of the sensory endings, and you're going to have voltage-gated sodium channels, maybe some leak channels, sodium-potassium pump. And so we tested manganese on the preparation, and we found out that it decreased activity. What would barium do, for example? This is another idea. What would our zinc do, for example? Maybe it would block these stretch-activated ion channels and it can't open. That could be a possibility. So these are all like stretch-activated ion channels. It might block that. And we thought that would happen. That's what I thought was going to happen because we did these manganese studies past years. We actually found out we got a decrease in activity. So I thought zinc might do the same thing. and these mechanical forces open up these stretch-activated ion channels. Generally, they know that sodium and calcium goes in, but some blockers like cadmium can block this response. So we thought maybe zinc would do the same thing. There's many different types of stretch-activated ion channels. There's lots of different families. There's even ones in archaea, bacteria, algae, plants, fungi. Drosophila, notice there's nothing in crayfish or crustaceans because they haven't identified them yet. But these are the different types of stretch-activated ion channels. These are important for our function as well. When they record from different types, they actually can look at the kind of currents that go through. So they know there's a calcium current and a sodium current. That's basically it. Okay. And there's different types of these stretch-activated ion channels depending on the animal, but also different expression levels of them in different organs in your body. Interesting. So these stretch-activated ion channels can actually allow sodium, potassium, and calcium, as well as magnesium, to permeate these stretch-activated ion channels, and they've showed to have some preference for calcium as well. All right, and then in the humans, they actually started looking at these, and they found out that manganese can actually go through the channel too. So we thought, oh, well then it shouldn't be blocked by manganese. Maybe it'll actually help it to go through. So we gave these stretches and recorded from the nerve, and we got these responses, which is really interesting. If we had high calcium, we actually got a decrease in response, and normal calcium was fine. We did these experiments, and here's some move, hold, move, hold, move, hold every 10 seconds with 10 seconds in between, and we actually found out there was a decrease in background activity with high calcium, and it wasn't as responsive. And then we return it back to calcium, we get the response back again, and we see more activity between the stretches. Very interesting. So low calcium or high calcium actually decreased the activity. That was neat. And if we use low calcium, so here's the activity before, this is during the stretch, between stretches, we see that even between the stretches, activity became crazy. And during the stretch, we had a lot of activity with zero calcium. So maybe it's not the calcium coming through the stretch-activated channel so much as maybe sodium, but somehow the nerve became hyper-excitable with low calcium. This might be happening with our zinc. And so it's like no calcium. And so maybe by blocking this calcium somehow, it made the preparation think or behave as the same as no calcium. That could be the issue. This is what we might postulate. Okay, it's different in this crab leg than what we're doing in the muscle receptor organ, because we are stretching the strand versus the muscle that might contract and actually have an impact on the sensory endings. But anyways, we were wondering then, is it impacting the sensory endings, or is it altering the neural activity in the axon? So it could be that process. There's little cell bodies of these stretch-activated sensory neurons. Okay, so we wanted to test something else. We want to get rid of the effect of the stretch-activated ion channels and just see if the nerve changes its excitability. And so what we did is, it would be nice to be able to record from the cell body and see what happens there. But what we did instead is, but we recorded just the nerve without the stretch-activated ion channels, or leaving them there if you want to, but also stimulating the nerve so we can record the action potential traveling down the nerve in the opposite direction that it normally would travel into the animal from stretching this. And what we can do is to record these compound action potentials. So there's many neurons in this nerve, maybe 100 or so neurons. So this is the issue, that this is what's recorded to as a compound action potential. We're not recording a single action potential. We're not intracellular. We're recording from the field potential of many of these. So it's like many of these action potentials that travel down the nerve. We record the ensemble average of those. So these are called CAPs, compound action potentials, from maybe hundreds of neurons, okay? So this is what we did. We stimulated the nerve, recorded over here, and we found out what's going on. We also then cut the chordotonal organ out, so we only had the nerve. All right, so there's the prep, there's the nerve right there, dissected out, whole leg. There's the nerve there, dissected away from the leg, so we can put a suction electrode here, put another one there, we can stimulate down the nerve, and record the compound action potential. You can also move the joint, if one wanted to, and record the joint activity at the same time, recording the compound action potential. There's a suction electrode over here on the right, so we can record it. There's another suction electrode right here that's recording on the nerve, and now we can stimulate and record the response, and as well as activating these neurons in the background if we want to. All right. So what we've done is we kept that nerve in contact with the chordotonal strands. So these are the activity that's probably from the stretch activated ion channels. This is when we stimulate and we get a compound action potential. So take this and blow it up. That's what you get over here. This is the stimulus artifact right here. There's the compound action potential buried in here. And then maybe some smaller axons that are firing right there. Stimulus artifact, the same thing. This is zero calcium. Look what happened. The background activity increased. The compound action potential really didn't change that much, but we got a lot more spontaneous activity. So that's kind of interesting. All right, and so what's happening here is that in low calcium, we got this increased activity. It didn't really change the shape of the action potential that we stimulated. So if low calcium, maybe we're removing this block here. The low calcium that's coming in normally through calcium channels is that it's not activating the calcium activated potassium channel, so it doesn't come back down, it doesn't hyperpolarize as much. And barium can come through the calcium channel, but it doesn't activate the calcium activated potassium channel. So this is interesting. So you could still get a barium current, but if barium comes in, it's not going to behave like calcium. It can't activate the calcium activated potassium channel. So that's kind of interesting. And these are just pumps that help maintain the calcium outside. So what we did is we took this is the number of spikes when we move it during the movement. We have the normal calcium, but we added barium, 15 millimolar, and we didn't really see any change. Now we took zero calcium, but in the presence of 15 millimolar barium, we didn't see too much change in the activity. So that's kind of interesting. And then if we take it out or take it back to standard saline and then go to zero calcium without the barium, we got an increase in activity. So it seems like that zero calcium really causes it to have some real activity that goes on. The idea might be zero calcium, kind of like maybe the zinc is blocking the calcium that comes in. It might change threshold from a normal. It might actually lower that threshold, and it might cause the action potential to become larger. The idea is that, for the sodium channels, that zero calcium that we're taking away the block, but if we're adding zinc, then it would continue to block it, so we might not get a bigger shape of the action potential amplitude. But if we're not activating the calcium-activated potassium channels by using zinc, because we're blocking the calcium that comes in, then the action potential might be wider than this one here. And if we don't have the calcium-activated potassium channel, then we're not going to see the hyperpolarization as we do normally. If you add more calcium, then you could see a bigger calcium-activated potassium channel current. It would change the shape of the action potential in a different way. So these are the ideas that we have. If we look at these caps, here's a stimulus artifact, here's a compound action potential. We take the 15 millimolar, which is stimulus artifact. This is just to get the compound action potential. We can take a minimal threshold, and it doesn't give too much. We always go to the maximum threshold to get the caps if we wanted to see how many compound action potentials we can get. But if we go to a lower level and keep that, and then we change the conditions like zero calcium, we can see if it becomes more excitable. This is maxing it out, so we can't get any more excitation. So we go to a sub-threshold of activating all the neurons, go to 0 calcium, and boom, you got all this activity that happens. And so that's kind of interesting. Spontaneous activity, as well as changing the shape of the compound action potential. But when we wash it back out and go back to this condition, we still saw some changes in that stimulus artifact. But the main point here is that neuron became hyperexcitable with 0 calcium. And so maybe that's what's happening with the zinc. All right. So when we tested manganese sulfate in past studies on this neuron, we actually found out that the background activity decreased. We think magnesium actually blocks the stretch activated ion channels. I thought zinc was going to do that. It doesn't seem like zinc's doing that because we still get hyperactivity, and so it's probably not blocking the stretch activated ion channels in the sensory endings, but maybe it's doing something on the nerve itself, acting like 0 calcium and not allowing the calcium activated potassium channel to work, and therefore it makes the cells more excitable. So I think that's what's happening with zinc. Okay, I know that might be a little confusing, might take some time to figure it all out, but it's basically relates to a lot of hyperpolarization. If we don't have that, afterwards the cell will stay, it won't stay as long in a hyperpolarized state, and it could be more excitable the next time. Okay, hopefully that helps a little bit.